Good afternoon and welcome to Advanced NMR Spectroscopy class. So today I will discuss about the NMR of dynamic processes. So I'll continue. So last class also I discussed about the same thing. So now let us see how to find out the rate constant. If you remember in the last class I told that you will be doing some NMR titration, okay? And then from that you will see the chemical shift difference. You plot the chemical shift versus the R, the concentration of guest versus host, the ratio is R, and you will get a plot, and then you have to do a simulation to fit your data. Now let us see what are the other ways to find out the rate constant. Okay. So I think all of you know what is double resonance experiment. So double resonance experiment what you do, you specifically select another field, radio frequency field. That's very selective, okay, and you either saturate or invert that particular frequency, okay. And so the whatever way that frequency was interacting with the other nuclei in the molecule will be now affected, or it will be modulated, okay. So this rate constant K, of course, all of you know that we are talking only about the slow region, because if it is fast, you will not see anything. In NMR, you will get the average thing. So the rate constant in the region of slow exchange, so that can be determined by the double resonance. And let us see how we'll go step by step and explain you how it is to be done. So in double resonance, as I told you, let us assume there are two spins. Okay, the two spins may be selected from a molecule. Okay, so let us say these are A and B spins here interact with which are changing their position. Okay, and they are slow in terms of NMR time scale. Okay, so how we'll find out the rate constant of this exchange? So for that, what you have to do is that so what you will see that so what you have to do that you, let us say you perturb the spin A, okay, so you can irradiate at nu A, okay. So this is your the B2 field. So B1 is common, B1 is for applicable, B1 is quite a very strong pulse, okay. It's a very weak, okay, it's very selective pulse, so you are irradiating at A, okay, with another field B2, okay, and then you will see that as you have irradiated, you are doing a irradiation on B2, you will see that the spins will get perturbed, okay. So if you are using a 180-degree pulse, the spins will get inverted or they will get saturated, okay. Now as A and B are interchanging, okay, because there is a through the reaction A to B, okay, as they are now, so automatically the information from A now will be transmitted to B, because as see in this equilibrium sum of A is getting converted to B, okay. So what, or sum of B is getting converted to A, so whatever you are doing on A will be reflected also on B, because they are interchanging. It's slow in respect of NMR time scale. Now let us see, there could be three situations. One situation is that there is no exchange. So that is the A and B, so there is no exchange. Okay. So now if there is no exchange, okay, so this I have written here K exchange is equal to 0. And if you irradiate, if you do the double irradiation on spin A, you will see that because you have done double irradiation, the spin A will get inverted, okay. And now once the B2 field is off, it will go back to its original value, okay. So it will recover through its T1 of, it will follow its own time constant. So it will go back to the again to the original value. Okay, following A, it's T1A. Now, another case is that where, let us say T1. So, let us say they are interacting. Okay, so there is exchange is happening. So what you did, that you inverted the magnetization of A from, you brought it to minus Z axis. Inverted means you brought it to minus Z axis. Okay, and we are telling that there is this K exchange, there is exchange. Okay, so that means there is there is a interconversion of A and B. And we are considering the T1. See, that T1 is a very important parameter. So let us see, T1 is very fast. That means before A is getting converted to B, it is again came back to its original position. Okay, so then in that case, so we are putting now T1 is very long. That means the recovery, the magnetization recovery is very slow. Okay, very slowly recovery. It's infinite time. Okay, so what you will see the major magnetization, whatever you are change you making A will be now transferred to B. And exactly that is happening. So when you are inverting A, you inverted A. Okay, now you see, because A is getting converted to B, so you will see the B signal is now decreasing with time. So this is your time scale. This is your time. Okay, so your signal of B is decaying, and with time the signal of A is recovering. Okay, so this is one condition. So you have a very long T1 for the nuclei. Okay, for this A nuclei, the T1 is very long. Okay, and you see there is a dramatic effect on resonance B. Okay, so the resonance B is now decreasing. The third thing is that it's a intermediate T1 value. See, let us say T1 is equal to 1 second. Okay, so that now you have there is a exchange is happening, and T1 is not infinite. Okay, so what you will see, that when you are giving a B2 pulse on A, you are doing a double irradiation at A, what you will see, because we know that there is an exchange between A and B, you see that initially the B signal will deplete. So this is your original signal intensity of B, so that depleted. Okay, and now once the B1 is turned, B2 is turned off, again it slowly goes back to our original thing. Similarly, here also you will see that initially got inverted, now it is slowly recovering. Okay, so that means when there is a slow exchange and T1 is not very small, you will see that if there is a exchange, if you do a double resonance experiment of any one of the nuclei, the intensity of the signal of the other nuclei will also be affected depending on the T1. Okay, if there is no exchange, the other nuclei will not be affected. If the T1 is very large, you will see there is a dramatic change. But if it is moderate, you will see that there is a decrease, and then slowly it will recover due to T1 relaxation. Now let us say I have taken one example. So the example is the 2-hydroxyacetophenone. So this is your 2-hydroxyacetophenone, and this is your 2-hydroxybenzaldehyde. Okay, and these two hydrogens, this red hydrogen of acetophenone and blue hydrogen of 2-hydroxybenzaldehyde is now exchanging. So this hydrogen is now going to benzaldehyde, and this blue hydrogen is coming to now acetophenone. Okay, and let us assume this is slow in terms of NMR time scale. Okay, so now you are selecting the B2. So B2 you are selecting. So we will write that this is your A, this is B. Okay, and you are doing a double irradiation on this. On 2. Okay, so B2 is turned on the new OH of the salicylaldehyde. Okay, and you are now measuring the intensity of the OH of 2-hydroxyacetophenone. Okay, so as they are exchanging, so as soon as you turn on the second magnetic field or double irradiation at the frequency of B, you will see. So this is the initial magnetization of A. A means your acetophenone. Okay. 2-hydroxy acetophenone. Okay, so initially that was the magnetization. As soon as you start decoupling at B, you see the A signal is now decaying. Okay, so it is decaying and decaying, then it will reach to equilibrium. It cannot become zero. Okay, because there are two processes involved. First thing is that the T1 relaxation, we have considered that T1 is not infinite, so your T1 is relaxing and some of the B nuclei is also getting converted to A. So you will get a, so that is a called equilibrium value, and you will see up to this. So this is your called the assume that this time, and that will require a time of infinite time. Okay, so assume that it is Ti. So you get a equilibrium magnetization of MZA. Okay, and we put that as a MZA T infinite, and you will see that again this is also MZA. This is also MZA at a particular time T, which is not infinite. It is a particular time, but this value will call as infinite time. See, there is no further change. Now, as soon as you are turning of the decoupler, which is fixed at B, you see that now the A signal also recovers following its relaxation time of acetophenone. Okay, it goes back to again to its original value. Okay, now let us see from this information how to find out the rate constant. Okay, I hope this part is clear. So see, we are trying to find out the rate constant, how A is changing to B. So automatically we are putting the double, we are doing a double decoupling experiment, choosing the frequency B. So automatically due to that, initially there will be decrease of the signal intensity of A, and then it will be a remain constant. That will call that MZA T infinity. And then once you turn off the double is the second decoupler, you will see the T1 signal is also recovering. Similarly, the T2 will also recover. For the B also the signal will be recovered. Now let us see. There is a little bit of mathematics here. Okay. So now you have to there is one thing called the lifetime of. We call that there are two lifetimes for, let us say, for A nuclei. One is called the observed lifetime. Another is its lifetime. Okay, that is the lifetime is related to its rate constant. You can see that Ka is equal to, so we call that is the lifetime of Ta. Okay, tau A, that is 1 by Ka, and this is the observed lifetime. Because why it is different? Because in observed lifetime there is some contribution which is coming from the B nuclei. Either it is increasing the signal or decreasing, depending on where you are putting your second decoupler. Okay, so that is, and how they are related, and also the A nuclei is also having a its characteristic the relaxation time. So that is T1A. Now how these things are related. So this is 1 by T1A, tau 1A is equal to 1 by T1 plus 1 by TA. Okay. Okay. So now how will correlate this? This is your equilibrium magnetization. This is your magnetization when we have done the decoupling experiment, and that is the equilibrium magnetization after decoupling at B. So how they are related? So this is the relation. MZA at T is equal to infinity. Infinity means this value. This MZ is nothing, is the signal intensity. That is directly related to the signal intensity, is equal to M0A. M0A is this value. This is this signal intensity. Okay, so that is related to the M0A into this, the ratio of tau 1A by T1. Okay, but let us say at any time. Now this is, we are talking about the when the magnetization, this magnetization has reached to the equilibrium value. Let us say at this position it is not equilibrium value. So at that time, how we'll find out? So at a particular time T, MZAT is equal to M0A and into there are two factors. One is the time factor. Another is the factor which is coming due to the exchange. Okay, and that has been now, and if you see that this part is getting, so automatically it is becoming m0a into a constant exponential minus t by t1a plus this. Okay, so now you rearrange this equation and finally you will get that ln mz minus ln, minus mz equal to infinity versus t, and if you do that plot you will get a straight line and whose slope is minus 1 by tau 1a. Okay, as I told you that mz is nothing but this signal intensity from here to here. mz infinity is the signal intensity from here to here. Okay, so you can get that ratio. Okay, so and then you know at this is your time scale, this is your time. So once you plot that, you get this. Okay, so this is your experimentally measurable value, and this is your time, and you can find out the observed lifetime of this, and from there you can find out by the rate constant. Similarly, you can do the same thing for tau 1b by irradiated signal at A. Exactly same thing. We have irradiated at B, you do the irradiation at A. So you will get the tau 1b. This part is clear, so one can find out the rate constant. Once you get this 1 by tau minus 1 by t1 tau 1a, you can find out the rate constant. Now let us see how to, so this is one way by double decoupling. Okay. Now you can do the same thing in a 2D NMR. So what we will do is that we will do it, that particular experiment is called the 2D exchange spectroscopy or EXSY, XC spectroscopy. Okay. So in earlier experiment was a 1D double resonance experiment. Okay. So now it has the same, so in 2D means you will have a pulse sequence. So here we will be using the same pulse sequence which has been used for NOSI. Okay. So if you remember what Professor Jesus taught you, is the NOSI pulse sequence is you will give a 90-degree pulse, X pulse, and then there will be evolution time for T1 that is variable. Okay. This T1 is a variable. So this will give you one dimension. When you do the double Fourier transform, it will give you one dimension. The F1 will be coming from this T1. So that's why it is a variable. Then you give a 90-degree pulse from the x-axis. Okay, and then you give a mixing time Tn. It is a fixed time. Okay, mixing time. Okay, it's a fixed time, not like T1. Okay. So mixing time means if there will be now interaction of the spins, okay? So that information will be coded. And then you will give, so when you do this, your magnetization will not be in the XY plane. So you have to bring the magnetization, they will be along the Z axis, okay? So you give another 90-degree X, so it will bring to the, again, the magnetization into the XY plane, and then you do the FID. So you will get the T2 domain, time domain spectra there. So if you do a Fourier transform, you will get F1 from this value and F2 from here. Okay. So that is a standard 2-dimensional NMR experiment. Okay. So if there is a dynamic process, and if the process is slow and there is exchange between resonances, then you will see there is a cross peak. Okay. We will see how the cross peaks are generated. Now let us see what is happening. So you are giving a 90-degree, now you are giving the first, this is the pulse sequence I have shown you. Okay, so you are giving a 90-degree X pulse. So when you give a 90-degree X pulse, what happens? It brings all the magnetization, let us assume there are two spins, A and X. Okay, so it will bring both the spins into the Y-axis. Okay, so it will produce and the magnitude will be MYA and MY X. Okay, so they are coming here. Okay, now you are giving a T1. T1 is a evolution time. So during this time, what will, because we know that A and X. So it is a frequency of nu A and it is nu X, and they are not equal. Okay, so they will now evolve depending on their offset. You see that X is here, whereas during that particular time, see, it depends on the time. If your time is 0, both of them will be at the y-axis. If, let us say, time is 1 second, so depending on their offset, they will move. Okay, so let us say at a particular time, due to their offset, the X nuclei is here and Y is here. Okay, now you are giving another 90-degree pulse. Okay, along this only. You are giving along this. So what it will do? It will bring this magnetization to the minus Z. You can see it has brought the minus Z, and this will bring to the plus Z. And same thing you see. Okay, so now you are giving a mixing time that is fixed. Okay, so as if there is any, if now there will be a transfer, because these two are changing positions. Okay, A and X are changing position, so there will be now exchange of magnetization between these two, and okay, and then automatically what that will do, what that means, when they exchange the magnetization, the magnitude of these two will be modulated. Okay, and then you cannot detect when the magnetization in the along the Z axis. You give again another 90-degree pulse. So depending on their this thing, so this will come to the this axis, and this will go to the minus, and then you record the FID. Okay, so whether it is coming here or here, it does not matter. So you will get the signal. Okay, so that is okay. So so the most important thing is that during this mixing time, the dynamic process, there will be a magnetization transfer. Okay, and that will give you the cross mix. Okay, now let us see. So normally this mixing time is kept around 1 to 2 seconds. Normally, most of the time you will see a couple of examples. Then you will see that mixing time is around 1 second. Okay, so this transfer rate during this mixing time is a function of the rate constant of a particular dynamic process. Okay, and but also the magnitude of the Z magnetization which is present at the up to this. It is only we are considering the evolution. The spins, depending on their offsets, they have moved. So, but during that also there is some relaxation, okay, and some exchange. So that will not be considered. So when you give a 90-degree pulse, at what time? What was the MZ? That is important. Okay. So that is the thing. The magnitude of the Z magnetization which is present at the Tm is equal to 0. So at this point, what was the magnetization? Okay. And then this will be, and what is the value of Mz here? That will depend on the T1 value. See, if the T1 is very short, this will be almost equivalent to your M0Z. But if T1 is very large, there will be drastic reduction of the magnetization. Okay. Okay, so thus the magnetization transfer is T1 dependent, and the signal of exchanging nuclei are amplitude modulated automatically, na? Because if the magnitude, see, if the T1 is short, your amplitude will be more here. If T1 is long, this small T1 is long, you will see the amplitude will be less. So that will give you the cross peak in your 2D spectrum. Okay, so we'll see that how it happens. Okay, I will take a real example. Okay, let us say this is a molecule. Okay, so this is a N-cyano compounds. So there are two methyl groups here. Suppose there is no exchange. Okay, so this part is, let us forget this side. Okay, so you see only that A is the molecule, there is no exchange. What you will see? You will see two methyl resonances, CH3A and CH3B. Okay, because this they have different chemical state. Their chemical environments are different. So you will get only two singlets due to methyl A, one for methyl A, another for methyl B. But what is known that this molecule, this center, because of the nitrogen lone pair, so there is a inversion. Okay, so due to this lone pair inversion, so this Cn comes to the other side. So once the Cn comes this side, now you will see that these two methyls are having, again, these two methyls are different, but these C and D methyls are also different from methyls A and B. So if there is a slow exchange happening, you will now have four different kind of methyls: A, B, C, and T. Okay. Okay. So now you see, when the 2D axis spectra was measured at minus 33 degrees centigrade, so it is the temperatures to ensure that the process is slow, the exchange is slow. Okay, and that is a solvent. Okay, and this is your mixing time. Okay, so you will see that now this is the 2D axis spectra, and you see that you have the four methyls, 1, 2, 3, 4. So you can see these are their chemical sheets, 3 and 4, and you see now there are two cross peaks. This is one cross peak, and there is another cross peak. Now you see that there is a cross peak between 1 and 4 and 2 and 3. This indicates that 1 and 4 are exchanging position. Similarly, 2 and 3 are exchanging position. Okay. But if you make the increase the temperature, okay, you will see that now there the exchange is very fast, and you will now get two singlets. You will get two singlets now. One will be average of this and this. The position will be average of these two positions. Other will be the average of these two positions. Okay. So in the slow regime, you are getting 4 peaks. In the fast regime, you get 2 peaks, and that will be the average. And I am dividing by 2 because all of them are having the same number of protons. Okay, that's why. Okay, now how will find out the rate constant from this 2D NMR? Okay, so the volume intensity of the cross peaks. So these are your cross peaks. Okay, so actually cross peaks are actually a cross sectional thing. Okay, so they are also having, one can integrate these cross peaks. Okay, that tells you what is the volume. Okay, if you do integrate, you will get their volume information. Okay, so this volume intensity of the cross peaks yields information about the rate constant. Okay, okay. So for slow exchange between two equally populated sites, okay, in this case there are two equally populated sites, Pa is equal to Pb, and the absence of scalar coupling. See, here also there is no scalar coupling. Okay, so the rate constant can be calculated from the intensity ratio of the diagonal to cross peak. So these are the diagonal peaks. So this is one diagonal, and these are the. So if you can integrate that this, because these are also contours. So you can integrate the signal of the diagonals and signal of the cross peaks also. So, and if you say that the intensity ratio, diagonal intensity ratio of diagonal to cross peak IC and the mixing time Tm, then you will see ID by IC, the relative ratio will be 1 minus the rate constant into Tm divided by rate constant into Tm. So from there, if you do the rearrangement, you will find that K will be equal to 1 divided by Tm into ID by IC plus 1. Because this ID by IC you can find out from the integration of this diagonal peak and cross peak, and Tm you know, because that is your experimental parameter. So you can find out what is the rate constant. So this is the another way one can do it from 2D spectra. Okay, so I'll tell here about the product operator formalism for this XC experiment, because this has also been taught you by Professor Hosur. Okay, so you have seen the pulse sequence 90 degree, T1 90 degree, Tm 90 degree, T2. Okay, so let us see what happens to when you are giving this. So this is your initial magnetization along the Z axis, IZA plus IZX. Okay, now you are giving a 90 degree X pulse. Okay, 90 degree X pulse. So that is applicable to both A and X, and it is bringing the magnetization along the Y axis. Okay, IYA, IYX. Okay, now what you are giving A, you have a T1 time. T1 is a variable or evolution time. So that what is the operator for that? That operator is called omega A T1 IZA plus omega X T1 IZX. Okay, so that means during this time, this magnetization will precess around the Z axis as per their offset frequency, and that is so what is that? Due to that, what are the magnetization? This IY, so you will have a cos omega 1 IY A cos omega AT1 IY I then, so this is the this is the Y component magnetization due to spin A. This is the X component magnetization due to spin A. This is the Y component magnetization due to spin Y, and this is the X component magnetization due to spin X. Okay, so that also Professor also clearly told. Okay, now you are giving your second 90-degree pulse. Okay, and you are giving again along the X axis. So what it will do, you will see that all these magnetization along the different axes will now be changing their position. So that thing has been represented here. So they are going to the, depending on their this T1 value, either it will be along the minus Z axis or plus Z axis, that I have shown you in the diagram. Okay. And then during Tm, that during the mixing time, there will be a exchange of the magnetization. IZA cos omega A T1 will exchange with IZX cos omega X T1. Okay. So what you see, the part of the magnetization which passes during T1 with omega 1 will be modulated during T2 with cos omega X T2. Okay. So which one is precessing with omega 1 during T1 will now be precessing as omega 2 during T2. Okay. So what that will give you? So now you will get a cross peak due to omega A, omega X and omega X, omega A. So that's why you will get the cross peak. Okay. So, but now I told you the pulse sequence is same for Xe spectroscopy as well as NOESY. Everything is same. Then how will distinguish the NOESY and Xe spectroscopy, whether it is a NOESY peak or Xe peak? So for that, you have to do a phase sensitive NOESY spectrum. Okay. So if you do a normal positive NOE, you will see the NOESY diagonal and cross peaks have alternate side. Okay, if your diagonals are of positive, you will see the cross peaks are of negative. Okay, so there will be a phase difference. Okay, but for Xe spectroscopy, you will have the same scene, same observation. Okay, you will see that the sign of the cross peaks are same as that of the diagonal peaks. Okay, I'll show you one example here. Okay, so you can see that this molecule is having both NOESY cross peaks as well as Xe peaks. Now you can see there is a color difference. See, because in NMR you cannot see, you only see the color difference. How will make the phase difference? It is given by some color. Let us say you are giving a red color to positive peaks, and you can give the negative peaks as a blue color. Okay. See, once you select one for a particular phase, one color, you cannot give the same color to the other phase, different phase. You can make the blue this one, and that will become red, or you can give a gray color and other will be black. So here it is a gray color is your diagonal peaks, and you see the NOESY peaks are all black color. Okay, so they are of different phase. But if you see in this region, you have cross peaks which have been expanded here. You can see. So you see now there are exchange peaks. You can see a exchange peak here. You can see exchange peak here. You can see exchange peak here. So you see that this one and this one are exchanging, this one and this one are exchanging. Similarly, this one and this one are exchanging, and this one and this one are exchanging. Okay. So you see, mostly your nosy interactions are coming from this side to this side. Okay, from your uphill region. Okay, whereas XCs are coming at the very, these are the positions, the protons are very close, chemical shifts are very close. Okay, so that is the way. So if you record a phase sensitive nosy, okay, you can distinguish the XC and C. In the same molecule, you can see, you can tell. Okay, so that is the only thing. So these are the information you should have, your knowledge about your structure, whether there could be some exchange peaks or not. Okay, let us see one more example, so that will be very clear. Okay, let us say you have a benzene ring and two para positions. You are putting a hexane chain. You are tying the two para positions with a hexane chain. Okay. So now if you see that it can, if you, and here the R is equal to methyl esters, okay, and these two are hydrogens. Okay. Now if you see under normal circumstances, if you consider it is a very symmetry, okay, then you see that all these things will be HA and HB will be identical. Okay. But if you see that these two structures, okay, if you properly number them 1, 2, 3, 4, which I'll show you in the next, you can see that when the methylene groups are at this side, this will have a different chemical environment compared to this. Okay, so but if it exchanges, you will see now that this hydrogen will have a very chemical shift like this, and this will be having this thing. So if the process is slow, you will see a AB type of spectrum, because there are two types of hydrogen. Similarly, you will have two methyl esters also. I am not talking about methyl esters. Okay. Now, if it is very fast, if this is happening, the rate constant is very large, then you will only all these things will average out, will give you only one type of hydrogen. Okay, it will give you a two type. Two hydrogens are equivalent. Okay. Now see, this has been observed. Now, if you see that at room temperature, so here both this is the calculated spectra. Since calculated spectra is calculated, if you remember last class I told about the line shape equation. So using that line shape equation, this is the calculated spectra, right hand side, and this side is the actually observed spectrum. Now you see that because if it is a AB spectrum, these two hydrogens are not equivalent, then you will see a coupling between them. So that exactly, see, this A is becoming a doublet, and B is also becoming a doublet. Okay, you can see this is JAB. Okay. Now as you see, that you are increasing the temperature. So if you consider that, let us say this is nu B and this is nu A. So nu del nu is much greater than JAB. Okay, so you see that now you just slightly increase the temperature. So you see that the coupling constant is now getting averaged out. Okay, because they are first in terms of NMR times. If you remember, I told you the three things. There could be three things according to the. So all time constant will not be same. One thing is the chemical shift. Second thing is the coupling constant. Third thing is the 1/T2, the transverse relaxation time. Okay, so that all these things get averaged out. So with respect to this, still as per chemical shift they are slow, but as per coupling constant they are quite fast. So that's why they have now merged and we're getting averaged out. And as you increase the temperature, now you see there is at a temperature where now both the peaks, it is very close. It is the rate, the K, okay, is nearly equal to, okay, so we call that as a coalescence point. Okay, so two peaks merge together, and now you further you increase the, it becomes now a very fast exchange. So you get a single line. Okay, now so you can find out the different parameters. So if you plot, if you, as I told you, if you plot ln k by t versus 1 by t, you will get a straight line. And from that straight line, you can find out the enthalpy of the barrier for this exchange, as well as entropy of this exchange. Okay, and one can calculate, if you put these values, exact values for delta H is equal to 43.3 kilojoules per mole, delta H is minus 51 kilojoules per joules per Kelvin per mole, you will get the delta G value at particular temperature is 58.5 kilojoules per mole. Okay, so one can find out this. Now let us see what information you can get by 2D. Okay, so that was using the Eyring plot. Okay, now let us see what happens due to these conformational changes in the CH2 chain. So we saw that there is a change in the conformation in this CH2. See, there is a change in the conformation. Okay, so this side is coming this side and this is coming this side. And this is more or less happening. You can think that these two carbons are fixed and there is a rotation around this bond. Okay. Okay, so this you can mark them as a 1, 2, 3, 4, 5, 6, and 7. Okay, so you can see that no, sorry, this will be your yes, I have given it. Let us give a numbering. We will put this as a 1, 2, this is 3, this is 4, this is 5, and this is 6. So what you do, you keep the position of 5 and 2 fixed. Okay, and then you rotate these 3, 4 bond. Only one bond will rotate, you will get this configuration. Okay, or this conformation. Okay, so here I have shown the 400 megahertz 2D exchange spectrum or XC. It is shown here. I will explain that with the XC pulse sequence. Okay, and mixing time was kept at 1 second. Okay, now let us see. So you can see they will explain the cross peak. So you will see a cross peaks are observed between those methylene protons which becomes identical. Okay, that means the methylene protons which are exchanging positions, and by this process they are becoming equivalent. You will see cross peak. Okay. So now for that only we told you that you are keeping the C3C4 bond. So you are rotating this bond. You are fixing 5 and 2. So if you do that, you will see that your 1 and 3 peaks. You see the peaks you see here, proton 1, okay, and your proton 3, they become equivalent. Your proton 2 and proton 4 become equivalent. You will see your proton 5 and proton 9 become equivalent. Proton 10 and proton 11 become proton 10 and 6 and 10. 6 and 10 become equivalent. And then you'll see 8 and 11. Sorry, this 8 and 11 and 7 and 12. Okay, and you can see clearly exactly the same way. You can see that 1 and 2. So this is the chemical shift of 1 and this is the chemical shift of 2, and you can see it is between 1 and 3. So this is the chemical shift of 1, this is for 2, this is for 3. You see there is a cross peak. Nice cross peak between 1 and 3. Okay, so 1 and 3 you saw, so they are becoming equivalent. Then 2 and 4, so 2 and this is your 4, so you are getting another correlation here. Then you have the 5 and 9, so this is your 5 and this is, so this is your 5 and this is your 9. This is this is 5. Oh, this is 10. This is your 5. Okay, so 5 and 6 are here. You see, 5 and 6 are overlapping. So you can see that again, both. So 1 is coupled to 8. So 6 is, you can. So this one is, okay. Now let me see. 5, this is your 5 and this is your 6. So 5 will be 2, 9. 9 is this. So 5, this is your 5 and 9. And then 6 and 10. So this is your 10. See, this is your, okay. Then 7 and 12. So this is your proton 7 that is connected to 12. Okay, and then last one is 8 to 11. So 8 is here. So they are very close chemical shift. So this is your 8 to 11. Okay, so you can see that tells that there is the one, that is the positions are exchanging, like 1 3 exchange is happening, 2 4 exchange is happening, 5 9 exchange is happening, 6 10 is exchange is happening, 7 12 and 8 11. Okay, and now from this, the volume information of the diagonal peak versus cross peak, you can find out to be the rate constant. Okay, that I have already told you how to find out. Okay, in the previous example. So one can find out the this kind of conformational changes by 2D XC spectroscopy. Okay, so there is another type of a chemical reaction. This is related to a organic reaction called 3,3 sigma-atomic reaction. Okay, if you see this molecule and these molecules, you cannot distinguish them. Okay, so these are called the invisible reaction, as the products are identical. Okay, so how to know whether the reaction is happening? Okay, so if the reaction is very fast, you will not be able to see. You will see the average spectra. If the reaction is slow, you will be able to see. Okay. So for this, this 400 megahertz 2D XC spectroscopy was recorded at -7 degrees. Normally, these reactions are quite fast at room temperature. And if you do these things, now you see that if you see that these two hydrogens, okay, they will exchange the position. In this case, the H9 will become H7 and H7 will become H9 in this structure. In this structure, H10 will be the H8 in this structure, and here this H8 will become H10. Okay. So that means you will see a cross peak or exchange peak with this hydrogen H8, H10 and H7, H9. So now if you record the NMR spectrum at low temperature, you see that your H7 is coming here, H8 is coming here, and you have the H9 is coming 9 is here and H10 is here, and you can see the H7 and H9, there is a cross peak. So that clearly tells that H7 and H9 are exchanging position, and H8 and H10. So this is the H8 and H10 are exchanging positions. Okay, just by recording a proton NMR at room temperature, you cannot tell, because both the structures are same. So how will say whether there is a reaction is happening? Because there is no other substituent. So such type of reactions, when there is apparently no visible change in the product structure, okay, you will see that the 2D exchange spectroscopy gives you very nice information about the reactions. Okay. Now another example, very similar example. Okay. So this is this 2,4,6 trinitro methyl aniline. Okay, in methyl aniline. So what you see, So if you see that this molecule, if you record a NMR, you will see these two hydrogens are equivalent. Okay, but if you take the resonance structure of this, it can be these two. There could be two structures. See, in one case, you will see that these hydrogen and see it is because these two structures are not equivalent. So that means the hydrogens are changing position because of the change in the methyl position. As the methyl position is changing, these two hydrogens are becoming not equivalent. So they are becoming a kind of AB type. So at room temperature, if you record the spectrum, you get this as a A2 spectrum. Okay. So again, this is the calculated spectrum and this is the recorded spectrum. So if you record at room temperature, you get a single peak. Now you are decreasing the temperature, so automatically you will see the peaks will become broad. And this you can say this is a coalescence temperature. Okay, minus 34.6 that okay become. And now you see that they have started becoming one peak to two peak. So it is slowly they are coming to the slow exchange regime. Okay, and see slowly as you are decreasing the temperature, the peaks are becoming sharper, and now you can even see the coupling constant, the nu and nu b, the coupling constant, JAB. Okay, because now yeah, they are becoming into even the slow exchange regime with respect to the coupling constant. Okay. So they can be very nicely studied by 2D exchange spectroscopy. Sorry, 2D XC spectroscopy. I will not show that. Okay. So another very interesting class of this thing is the cycloexchange, the axial equatorial, where you can see at low temperature. So what they have taken, it is a D11. Okay. And hydrogen, there are, see in cyclohexane, there are, it is C6H12. So there are, it is a 66D11H. अरे कुछ बोल रहा है, पुअर नेटवर्क बोल रहा है, देखो आ जाएगा ना. Okay. So there are one hydrogen. So that one hydrogen can be equatorial or it could be axial. And we know that already from our chemical sheet anisotropy, the axial hydrogen appear in the upfield, whereas equatorial downfield. So now you see at very low temperature, at minus 89 degrees centigrade, you can see clearly the equatorial hydrogen and the axial hydrogen. Okay. And because the deuterium coupling is very weak. So you can see there is a little bit broadness that is due to the deuterium coupling. Okay. Now as you are increasing the temperature, the lines become now broad and finally they coalesce and then they become a single peak at even at minus 4. So above minus 49 degree, you means above minus 63 degree, you will start seeing only one peak. Only if you increase the temperature, the peaks become sharper and sharper. Okay. So up to this is your slow regime axis. This is the intermediate, and this is your fast. This and above. Only if you increase the temperature, your peak will be sharper. This is also a very interesting reaction. This is also a very pericyclic reaction. See, in all these cases, if you see here, both the peaks are of equal because both the position, the PA and PB is equal to 1. PA, the fraction of A and B is equal to same, because 0.5. Okay. But there could be cases where it could be different. I have taken one such example. You see, this is a reaction. This is a trine system, and if you they undergo thermal electrocyclic ring closing to give you such a product. Okay. So if you record a room temperature NMR, you will get an average spectrum. Okay. You will get an average spectrum because it is happening at the very fast in NMR time scale. Okay. You see, even at minus 73 degree, you get one peak. Okay. But if you start reducing the temperature, you see that initially the peaks become broad. Okay. And then you can now see that there is a hump here. And then as you are further decreasing, you get two peaks due to two structures. Okay. and now their ratio you can find out. Okay, this happened. This is due to because the ratio, it depends on the energy of these two structures at a particular temperature, that is governed by the delta G is equal to minus RT ln K. Depending on their energy, the equilibrium constant will be dependent, and now they are nicely separate. Okay, so this is the way you can find out. So I have finished my presentation, and this is your last class regarding your material. Now Monday I will discuss about discuss with some problems. Okay, but still, if you have some doubt, you can ask me on Monday. Okay, Monday will be your last class. Okay, and then Monday also I will give you one assignment that has to be submitted. Okay. If you have any doubt, you can ask me a question. Now you can send email or you can ask me on Monday. From any other, I have told several times, from any other topic. Okay, but you please mention the lecture number when you ask.
Prepare for the exam.
And also prepare for the exam. Your tentative exam will be at the middle of June. Okay, data will let you know. It will be the middle of June. Hello?
By next week, we will put a circular.
Yeah, and next week a circular will come with in regard to this. Okay, so Monday again we will join at 4 o'clock.
This is the last class. Try to join.